Welcome, listeners. So, here again we have gathered for the next discussion in the series of lectures on the fundamentals of geology. And I am Dr. Shanti Banerjee, a faculty member in the Department of Geology, Banaras Hindu University, Varanasi. So, the next topic that we will be discussing after the formation of minerals in the last lecture. In this lecture, we will be discussing on the classification of minerals. So, like I was saying in the last lecture, that obviously minerals are the constituents of any rock that we can see around us, be it your granite or basalt that make up the crust, be it your periodicite that make up the mantle. So, now looking at minerals, there are broadly there are two kinds of minerals. The first one is a silicate mineral or the group of silicate minerals, and you also have non-silicate minerals. So, this classification and categorization is so important that means you can say in a pattern like this that you means either you are a silicate or you are not a silicate one. So, this is so distinct and it is so important to group different rocks that we see around us. So, broadly speaking again, if you are looking at the silicate minerals, there are certain silicate minerals that are included in the broad group of your silicate minerals. There are certain minerals which are relatively less in volumes. Right, talking about volume, I can also say that almost 90% by volume of rocks that we see on earth is dominated by silicate minerals, and only again talking about volume, only 10% of the rocks have constituents of your non-silicate minerals. So, we need to definitely understand that what are silicate minerals and which are not silicate minerals. But before that, before plunging into that discussion of silicate minerals and non-silicate minerals, what is again important is the understanding of silica tetrahedron. So, obviously, for any silicate mineral, your silica tetrahedron is the building block. So, how a silicate tetrahedron forms? So, if you simply look at this diagram, then you can see you have one silicate that is sitting at the center with your +4 charge in it, and you have 4 surrounding oxygen atoms that are present with individual -2 charge in it. So, now if I want to combine this, then with this Si with 4 oxygens, you can say that in totality it will have a charge of 4 minus, and it will be as a whole or in totality it will be considered as a silicon ion. So, now here also I would like to highlight that if silicon is having a +4 charge, and in case of oxygen you have individually you have -2 charge for the individual oxygen atoms. So, now if I combine this, you can see that this 4 gets separated or is subtracted from the 8 in total of -8 charge, and the total charge of this silica tetrahedron is 4 minus. So, this whole silica tetrahedron will have a you can say -4 charge in it. Now, why it is important? Because if you are having silicate anion with -4 charge in it, then it is actually free to bond with other cations. So, if I simply think of the most common cations that gets bond with it, there are 6 cations that are used dominantly to make up any silicate mineral. The first one is calcium, then you have magnesium, sodium, potassium, aluminum and iron. So, these are the 6 cations that will get bonded very easily with your this 4 minus charge silicate anion, and they might result into the formation of a mineral. So, here also I would like to take a very simple example from your chemistry labs back in your school life, that in your laboratory you might have seen always that your similar anions similar anion groups, they are kept together. Means, for example, if you are having some sulfates, they are kept together. If you are having some carbonates, they are kept together at some other place. If there are some nitrates, they are also kept together at some other place. Why it is so? Because if there are similar anions that are kept together, then the chances of reacting between the anions are very less. So the chances of having an accident in your laboratory is also quite less. But in case if you are having some sulfates and nitrates and carbonates side by side, and by chance if they get spilled upon your table or on your floor, there is a risk of accident, or means be it a simple fire or some other kind of reaction or fumes or gases that might result into some accident. So that's why you can also say in a manner here that anions like the silicate anion, they can easily bond with your cations, resulting into, here it is not a violent one, I will say, but here I can say that your silicate anion gets combined in with your cations, or be it calcium, magnesium, sodium, potassium, aluminum or iron, and they are resulting into the formation of a mineral. Specifically again, as it is dominated by silicate anion, so they are clubbed into or grouped under silicate minerals. So like I was saying that if you have this silicate structure, or this means you can say the silica tetrahedron or silicate anion as your constituent of your mineral, then obviously it represents the backbone structure of your various silicate minerals, including quartz and feldspar, which are the most commonly occurring minerals out of any other silicate minerals. So the understanding of this combination of silicate anion with the commonly occurring cations are extremely important for the understanding of the atomic structure or the arrangement of any mineral that we will see. Then again, broadly speaking about now silicate minerals only, we will talk about non-silicate minerals in the last part or the later stage of this lecture. So if I look at the rock forming silicate minerals that I was referring to, that 90% of volume of the rocks that are present on earth are dominated by silicate minerals. So here I can say broadly again, the silicate minerals can be divided into two categories. The first one is the ferromagnesium silicate minerals, the other one is the non-ferromagnesium silicate minerals. So simply, as the name suggests, you can say that ferromagnesium silicate minerals, they are dominated by the presence of iron and magnesium, whereas in case of your non-ferromagnesium minerals, they are not dominated by iron and magnesium, rather they are mainly dominated by aluminum. So in this case again, you can separate these two categories, ferromagnesium silicate minerals and non-ferromagnesium silicate minerals. Now if I look at the individual category, then in case of ferromagnesium silicate minerals, you have four groups of minerals that are present, again which are rock forming mineral groups. Not all, I will not say that these are the only group that are ferromagnesium, but these are the main rock forming ferromagnesium silicate minerals. So there is again a problem always that we go through, or commonly students they go through this kind of a problem, that group and mineral name, they are two different things. A set of minerals constitute a group of a particular set of minerals. So your olivine group is a broad spectrum of different minerals, out of which your olivine is the representative, or you can say the most commonly occurring mineral of this particular group. So the first group, that is your olivine group. Then you have the pyroxene group or pyroxene group also. Some people say pyroxene, you can also say pyroxene. So the most commonly occurring rock forming mineral in it is your augite. Then you have the amphibole group. Within that, again the most commonly occurring amphibole is your hornblende. Then you have the mica group, and here there are two kinds of mica. We will talk about the other one in the non-ferromagnesian lot, but in the case of the ferromagnesian silicate mineral, we'll talk about biotite. So, biotite is a ferromagnesium bearing or you can say ferromagnesium mineral within the broad group of mica group of minerals. So, you have this 4 group under your ferromagnesian silicate minerals. So, the minerals which are the most important mineral within the group are olivine, augite, hornblende and biotite. Now, coming into the second class of minerals or rock forming, that are non-ferromagnesian minerals. Here you also have the first one, that is your feldspar group, and it also contains 2 subgroups. One is the plagioclase subgroup, which contains minerals like albite and anorthite, and you also have another subgroup, that is your potash subgroup. That also signifies why it is potash subgroup, because the feldspar is of potassium type, and in case of your plagioclase subgroup, the feldspar is actually dominated by either sodium or calcium. In case of albite, it is sodium. In case of anorthite, it is your calcium. So, in the potash subgroup, you have a mineral that is orthoclase. Then the next group, that is your mica group, or you can look at the mineral in specific, muscovite. So, now you can compare between the ferromagnesian mineral within the mica group, that is biotite, and parallelly your non-ferromagnesian mineral within the group of minerals is your muscovite. And finally, your another or the most important non-ferromagnesian silicate mineral is your quartz, that is simply silica or SiO2. So, now these 9 minerals, olivine, augite, hornblende, biotite, which are treated as ferromagnesian silicate mineral, and non-ferromagnesium silicate mineral, albite, anorthite, orthoclase, muscovite and quartz. So, these 9 minerals you have to remember throughout your time with geology, or you can say means any academic pursuit related to geology. You have to always remember the name or these minerals, and also the basic characters, how they look, how they occur in the nature of these 9 minerals. Again, why? The answer is because again and again these are the 9 rock forming minerals which are the most means you can say the dominant constituent of any rock, or about 90% of the rocks, talking about volume of rocks on earth, they constitute the 90% volume of rocks that occur in the earth. So, again a small clarification here, only I will say this, this requires detailed discussion, but in a very simpler term, that why I can't consider anorthite, albite and orthoclase in this broad group of feldspar. The reason is that there are 2 subgroups, your plagioclase subgroup and potash subgroup, and they are divided due to a reason that whenever these silicate minerals are forming, what is happening, that there are chances of substitution between the cations. For example, when we are talking about anorthite and albite, there is a continuous substitution that takes place, which is also referred to as solute solution between albite and anorthite, and albite that is dominated by sodium cations and anorthite that is dominated by your calcium cations. And what chemists say, people from chemistry background, they say that if the 2 cations are having same charge, then the possibility of substitution between the 2 cations is more when the, you can say the radius or the means atomic radii of the cations are similar or within the limit of 15%. Means if the for example some cation is having some atomic radii of for example 10 nanometer, and the other one is having a 15 nanometer radii, then definitely there is a chance of your substitution among the cations. But if it is not having, though having a similar charge, but it is not having similar atomic radii or not within the 15% benchmark of difference between the atomic radii, it is not possible to substitute any other element. So that's why potassium is never substituted by sodium or calcium. That's why you have these two subgroups within the feldspar group. Otherwise, you would have directly one broad group of feldspar, and you would have this albite anorthite and orthoclase belonging to the same group. But due to this problem in the substitution, though there is substitution between sodium and calcium in case of plagioclase subgroup, there is no substitution possible in case of the potash subgroup. So that's why you have this two broad subgroups of your plagioclase group and potash subgroup. So again, just to conclude this particular slide, or means if I want to summarize still here on this discussion of ferromagnesian and non-ferromagnesian silicate minerals, then again I would like to mention, or you treat it as a statement that will be applicable if you study any rock on earth, or at least you are studying 90% of the rocks on earth. Then the rock forming minerals, specifically these 9 minerals: olivine, augite, hornblende, biotite, anorthite, albite, orthoclase, muscovite and quartz, they make up almost 90% of all the rocks that we can see on earth. Then looking at the silicate structure now, so that was about mostly about your composition of ferromagnesian silicate minerals and non-ferromagnesian silicate minerals. Now if I talk about the silicate structure, we have talked about the silica tetrahedron. So there are varieties of combinations you can see. The first one is independent tetrahedra structure, where these tetrahedra, they are not attached with one another, and they are only glued into space due to the presence of some other cations in between them. So you have an independent kind of tetrahedra structure. Then you have this single chain structure, which looks like this, simple bars of iron or bars of gold like this, and they combine to form what is known as single chain structure. We will look at different examples of it, but first we will try to look at the structure of the silicate. Then you also have a type that is double chain structure, when your two single chains are getting attached like this, and they form this kind of arrangement, means two gold bars, if I place side by side, they look like that, but they are placed on top of one another. So finally they will look like a structure of double chain silicate like that. Then you have the sheet silicate, where you have this circular kind of arrangement. I will not means I was referring to circular because it mimics kind of a circle, and hexagon is also you can say a most proximal geometry to a circle. So that's why you are having this kind of a hexagonal kind of sheet structure. We have also seen the presence of hexagonal crystals when we discussed about crystallography. If you can remember, when we talked about the structure of beryl, or talked about the structure of the quartz in case of hexagonal system. So there also you can get this kind of appearance, but this is different obviously, that is the crystal system. Here we are looking at the structure of the tetrahedron. So here you are getting this sheet kind of silicates, and they are also, so if you have this one sheet on top of one another, then these sheets they are attached, or they are combined with the sometimes your van der Waals forces of or they are bonded together through your van der Waals forces. So you can have this sheet structure on top of one another. Then you have this three-dimensional complex structure of tetrahedra. Again, this reminds me of the structure of your sodium chloride, which is obviously the mineral halite. Now if I want to group this kind of silicate structures based on the arrangement of the silicon and oxygen that make up the crystal structure, then the first group I can say about the nesosilicates, where you have a ratio of silica and oxygen 1:4, and the best example is your olivine and also garnet. Then you have your sorosilicates, which are your double chain silicates or double tetrahedra, where the ratio between silicon and oxygen is 2:7, and examples include epidote and zoisite. Then you have the cyclosilicates, that are the representation of your beryl or quartz or tourmaline. Here you have this rings or cycles of silicon and oxygen in a ratio of 1:3. Then you also have the single chain structure we just discussed about. In that it has a silicon oxygen ratio of 1:3 or sometimes 4:11, and the examples include your pyroxene. Then you also have your phyllosilicates, which are your seed silicates. In that case, your silicon and oxide, they have a ratio of 2:5, and examples include muscovite or biotite, like we have discussed under the mica group, the ferromagnesium biotite and non-ferromagnesium muscovite. These are all examples of sheet silicates which are broadly considered as phyllosilicates. Then you also have tectosilicates, which are also referred to as a framework silicate, which defines the framework of some minerals, for example quartz or feldspar, and it is having a silicon oxygen ratio of 1:2. So they define a three-dimensional framework of this silica tetrahedra. Now individually, if I look at the different groups, I will not go into very details of each and every mineral, but generally speaking, the most commonly occurring, like I was mentioning, that each and every group of minerals, they contain a very characteristic mineral in it. For example, we start with, if I am referring, and that is the mineral generally sometimes also used as the broad group name also, these mineral names are used. So in case of olivine mineral, you can see this is your olivine group, which is named after the olivine mineral. So it is having a general formula of magnesium Fe twice and your silica tetrahedra with it. So here the brackets is nothing but the means way of chemistry people who keep these cations in brackets, and they want to signify that when they are kept in brackets, that means one can substitute the other to form a different mineral as well. So here, if I am referring to two different mineral, then the magnesium silicate here that we are looking as an olivine is nothing but phosphorite. Similarly, the iron bearing olivine that we can think of is your phyllite. So there is also a solute solution, like I was mentioning about albite and anorthite, where your substitution between the two cations, sodium and calcium, is going on continuously, and it also has a range of minerals in it, starting from albite to means the two N members are your albite and anorthite. So it starts with albite and it ends with your anorthite. Similarly, in case of olivine also, you have these two N members of phosphorite, that is magnesium bearing, and you have the phyllite, that is iron bearing. So in this case, your solute solution will have this N members of phosphorite and phyllite, and this range of composition or the different minerals also occur in this solution based on what? Based on the ratio of the presence of the two cations, your magnesium and iron. Then you have the pyroxene group or pyroxene group. So that is also having a chemical formula, as you can see, XY and Si2O6, where X and Y, they represent these different cations. And again, in the pyroxene group, your augite is one of the most commonly occurring mineral. But apart from that, there are also there are minerals like enstatite, hypersine. So they are simply known as your orthopyroxene, and minerals like your augite, they or pigeonite, they are referred to as clinopyroxene, depending nothing but on the type of crystal system where they are crystallizing. So though both are pyroxene, in case of enstatite or hypersine, they are pyroxene, but they crystallize in orthorhombic system, like we discussed in crystallography, that different minerals, they crystallized in different system or different arrangement they possess. So if a pyroxene like enstatite or hypersine, they are having an orthorhombic structure in it, they are termed as orthopyroxene. If minerals like augite or pigeonite, if they are having the structure of the monoclinic crystal, or they crystallize in the means monoclinic system, they are referred to as clinopyroxene. So these are the two broad you can say subclass of pyroxenes, your orthopyroxenes and clinopyroxenes. So augite is a clinopyroxene, but the occurrence of augite is more in comparison to the rest of the pyroxene. So that's why again augite is, you can say, is a more important rock forming mineral in comparison to your other pyroxenes. So likewise you can have the silica tetrahedra chains of this structure, and your metal ions will occupy the space within the chains. So this is your augite under pyroxene group. Then you have the amphibole group, which again have this characteristic mineral, that is hornblende. So hornblende is looks like this in your hand specimen, and under microscope it looks like this, and it is having a tetrahedra structure, which is also referred to as your double chain silicates. So they are having a silica tetrahedra structure like this. Here also there is like simply, if I go by the general formula A, B, 2, C, 5, D, 8, you can see there is a long list of cations that are present in the structure of the amphibole. So here there are different sites where your different cations are getting accommodated. So these double chain silicates, where your silica tetrahedra form chains, and they share oxygen atoms with adjacent chains. So likewise they also form. Again talking about broadly about amphibole group, apart from hornblende there are other minerals like tremolite, actinolite. These are also minerals, they also belong to the amphibole group of minerals. But again speaking about rock forming mineral, again the most dominant rock forming mineral within the amphibole group is your hornblende. So if you take a rock is having some amphibole in it, so again in 90-95% cases it is a hornblende. Now coming into the mica group, and it contains again several minerals like muscovite, biotite, chlorite, it minerals like this. And also again this group gives you the two again most important mica minerals, the muscovite and biotite. Again I am talking about rock forming minerals. So again if I am looking at a rock that contains this mica group of minerals, either of these two, either muscovite or biotite are generally present, or is generally present in that. Apart from that, sometimes chlorite are also present, but if a rock is having mica group of minerals, then again the likelihood of the presence of muscovite and biotite is more in comparison to other mica minerals. So again you can see this general formula of XY2Z4O10OH, true hydroxyl ion is also present here, and these are the sites again which are occupied by various cations in it. So in case of mica group, the minerals will possess a sheet like structure that we have seen, and they get detached from one another. This book like a sheet like you can say planes of this mineral, they get separated very easily because of the weak van der Waals forces that are present within the sheet silicate. So they form individually, they are bonded very strongly, but across the layer they are bonded very weakly. So you can simply take out different sheets of be it muscovite or biotite from its structure. Then obviously you have the feldspar group, like we have discussed about the albite, anorthite and the potash feldspar as well, that is orthoclase. So this is orthoclase, this is your albite, this is your anorthite, and this is how they look under microscope also, but we will be dealing with this in a different lecture from I think 1 or 2 lectures from now. We will be looking at different minerals and how to identify them later on. Again just to talk about the framework structure. So your feldspar group will have a 3D framework structure composed of interconnected silica tetrahedron and also alumina tetrahedra. So it composed, like I mentioned, it is the feldspar group, it represents non-ferromagnesium silicate minerals. So it will not contain any iron or magnesium in its structure, rather it will contain aluminum, always aluminum tetrahedra in its structure. Then the final one, obviously the quartz, or it is the most commonly occurring mineral you can say, that is composed of silica, and it forms under your hexagonal crystal system, and you can see different types of quartz with different colors. Remember, these colors are generally controlled due to the presence of some other cations or some other impurities in it. So mostly if it is having some cation associated with the silica, some iron is present as impurity, then it will means it will gain some red appearance within it. So depending on means what kind of impurity that is present within in the crystal structure of your quartz, the color of that material gets controlled. So now for non-silicate structures, I'll say means that's all about actually your silicate minerals, that are rock forming silicate minerals. Now for rock forming but non-silicate structures, there are broadly you have hematite, you have halite, you have calcite and sulfide. Just to summarize it quickly, because they only contain, you can say, or compose 10% of the rock volume on earth. So you have hematite, it is obviously not a silicate one, you can see that iron and oxygen are the main constituent. Halite, that is your sodium chloride. Calcite, that is calcium carbonate, again that is not a silicate one, and also several sulfide minerals like galena or chalcopyrite, where you will your means element or your cations are combined with your sulfides, or so that's why they form the sulfide minerals. But remember that sulfide minerals are extremely useful when we will be also discussing some aspects of economic geology, that sulfide minerals, they also carry gold or silver or some other rare earth elements along with it. Then obviously you have different uses of calcite, like the powdery form of calcite are means used as agricultural lime in agricultural fields, and also obviously rock salt that we all eat, and we also have other uses of NaCl in industries as well. And last but not the least, obviously, or the first one rather, that is your hematite. It is actually hematite is one of the most important mineral that the means humankind have ever recognized, and it is the mineral which actually put the foundation from our stepping into from the Stone Age to the Iron Age, and we are still in the Iron Age till now, because any structure you can see around buildings, bridges, roads, highways or tunnels, everything are based on the structure of iron, which is extracted from the hematite mineral. So obviously it is an ore mineral of iron ore. So your non-silicate minerals, though they only contain, you can say, or compose only 10% volume of the earth or the rocks in earth, but they have great utility in our daily livelihood. And like I mentioned, be it hematite, halite, calcium carbonate, or the presence of sulfide minerals, they also are indicators of various, you can see, costly or various precious rare earth materials like I mentioned gold, silver, platinum, etc. So here I would like to end the discussion on silicate mineral and non-silicate mineral. Next lecture we will discuss or will talk about that how to identify the silicates or non-silicate minerals when we look at them on field, or when if you get a sample of that in your hand, how you would be able to recognize that whether it's a silicate one or a non-silicate one. Secondly, whether it's a ferromagnesium silicate mineral or it's a non-ferromagnesium silicate minerals. So we'll talk about that later on. Thank you.